YouTube. Why you listen to me on YouTube? That's a lot of it. She has an umbrella.
Here we're seeing volcanic eruptions. There's not a lot of sound associated with these. This is what we would call a violent eruption. This is magma or lava that's been blown to bits. You see some bits are smaller than others. This is ash, it's really fine. You will see some rocks coming out. Sometimes they call them car bombs or rock bombs. We don't really know how big they are because there's nothing to scale there, so they could be quite large. You will see volcanoes have their own weather patterns inside. It could rain, it could storm. And there's one you're going to see lightning. There you go. So there's so much friction and static electricity. This is a quieter eruption because it hasn't been blown to bits. This could become ash if it's very explosive. So basically you have that magma, it's blown to bits really fast and very violent, you get ash. So these eruptions, this ash is considered light in color. Well, that material's moving upward. Yeah. Pressure. Yeah. These are indicating they're pretty heavy because they're landing very close to the volcano. So you'll see all these different various eruptions. These are nice, they're happening at night. Those are big pieces of lava coming out. It's a little bit less violent eruption than a solid ash eruption because you still have those bigger pieces of lava coming out of the volcano. Notice the steep sides of the volcano and the violence of the eruption. Really steep sides, pretty violent eruption.
Do they have video of I thinking the volcano in Seattle?
Mount Rainier? Mount St. Helens?
Yeah, when it blew.
Yes.
They do?
Yes.
You watch it?
I don't think we'll get to it. Okay, so those are some different types of eruptions. So those are more the violent eruptions. But all volcanoes, whether the eruption's violent or quiet, has the same insides. So here's basically the anatomy of a volcano. You have the magma chamber. It'll move up the pipe. You can have side pipes. So if there's a weakness in this area, an opening, that magma will travel until it meets resistance and stops. Here on this sill, it moves sideways till it meets enough resistance and stops. It can solidify and seal that pipe off. This one here, it didn't meet resistance. It kept going, 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 flowed out, and now you have a side vent going. So anywhere you have a place where the magma comes out, it's now lava because it's on the surface of the earth. Where it came through, that area is the vent. So we have a vent here, and we have a vent here. You can have multiple vents. If this area, this side vent continued all the way out, you'd have another vent. So if this pipe moved all the way out, it would vent here. So think of your heaters, right? You have heater vents in your home, most of you, where the heat comes out, that's a vent. Same kind of thing. You have the crater. Once this magma and lava disappears, you'll get this shape right here, kind of a little U shape. That's a crater. You have your pipe. Now the colors, you'll see the black, the gray, the white, black, white, gray. This is just indicating different material has exploded or came out of the mountain. So let's see, this black could be normal lava, really viscous material, kind of thin, so it doesn't explode out into little tiny pieces. So again, a different kind of lava. Now ash. So it went from a quiet eruption to a really violent or more explosive eruption. And then back to quiet, more explosive. So these different colors just indicate different times the mountain has erupted. So here you would see it would be 1, 2, 3, 4, 5, 6, 7, 8 times. And a little bit 9, 10, 11 here. So those different colored layers are just showing you that the mountain's built over time, eruption by eruption. So make sure you know the insides of the mountain. Now we have two kinds of rocks. We have dark rocks and light rocks. And those are magma or lava that's cooled and solidified. So we need to associate the color of the rock with the type of eruption that happened in the area, or the type of eruption that is most likely to occur in the future. So anyone have any idea what the black rock, is this going to be a quiet or an explosive eruption?
Explosive.
Okay, and quiet or explosive?
Quiet.
Okay, so let's look at that. We were going with explosive and quiet.
Oh, no. Quiet. Quiet.
So what we have here is we have the magma. It contains minerals that compose the oceanic crust, this top one. The oceanic crust. We know we have the mid-ocean ridge and that divergent plate boundary. Is that an explosive thing that's happening at the mid-ocean ridge? Or is it more of a quiet thing that's happening? The mid-ocean ridge in Hawaii, okay, hot spots, any kind of that black basalt, that actually indicates a quiet eruption. So we want to make sure we're linking those two things together. We have the oceanic, it's dark minerals. We call it mafic, so any dark rock is mafic. Mafic just means it has more magnesium and iron in it, and it's darker in color. This one happens to be basalt, which is the lava and magma that's on the oceanic floor. It's pretty runny. Now down here we have continental minerals, mostly granite on the continent, but we also have other types of rocks that are exuded on the Earth's surface on the continents. These that are light in color in general, overall, light in color are considered felsic. Felsic is anything that's light. Now the color here comes from silicon. Silica, SiO2. Now these light colored rocks are going to be high in feldspar, which is a light colored mineral, and silica. So silica, remember, if you open up your beef jerky or you get a purse or shoes sometimes, you'll find those little packets, remember, and you open them up and it'll be that light colored mineral, almost see-through, little marble looking stuff. That's the silica. Higher in silica, lighter in color. Iron and magnesium are dark, so if it's high in magnesium and iron, it's going to be pretty dark. So make sure you associate mafic with the darkness, why? Felsic with the lightness, and why? So if we're looking at igneous rocks, which is just cooled lava and magma, we can look at these darker rocks. This one's even started to rust, which indicates it's higher in iron. So this is a darker rock. And this overall is kind of a light rock. So we have darker mafic, lighter felsic. So this would be associated with what kind of eruption? Quiet or explosive? Mafic, basalt, quiet. So the felsic, this here is felsic. Okay, it's lighter in color. It's going to be associated with a more explosive eruption because it's higher in silica. That's where that light color comes from. So you want to make sure that when you see pictures of rocks and you're asked to categorize them, so put the rocks that are going to indicate a more explosive eruption, you put your light colored rocks there. Put your rocks where you're going to have a quieter eruption, you put your darker rocks in that column. So you just need to be able to categorize them that way. Mafic, felsic, quiet eruptions, more explosive eruptions. So here we have an explosive eruption. So we have our felsic rock. So we have volcanic activity, molten rock down here, and you have lots of gases that are dissolved inside of magma. So it's how those gases come out of the magma will determine if you have a violent eruption or a quiet eruption. So if you have those dissolved gases and they're staying in the magma, that means it's building up pressure, 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 more gas, pressure, 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 and then it finally blows. Once it gets enough pressure, just enough, it'll blow. And that's when it can take that magma and just blow it to bits, like this ash. So the ash is really, really fine. It's like, imagine if you took powdered sugar and table salt and put it in your hand and mixed it. That's how it would feel. It's really, really fine. So that means that you had a really explosive eruption to be able to take that magma and just blow it to particle sizes that small, where it would feel really, really fine. So that means that you had a really thick magma. It had a lot of gases trapped in it, building, building, building pressure.
And if it has vents, will it make it like not as dramatic?
No. And I'll talk about why in just a second. Now imagine you can have 1 cubic foot of water, that's 1 foot by 1 foot by 1 foot. It can expand 4,000 cubic feet. So that cubic foot of water can expand to 4,000 cubic feet. That's big. Now you have water vapor that is in that temperature can get up to 1,200 degrees Celsius. That's hot. So remember, water boils at 100 degrees Celsius, so 1,200 is just, you're going to be done, like right away, if you come in contact with that. So when you see this ash right here, because it is very violent and explosive, what will happen is that ash initially might rise, because the pressure, and then boom, it can come racing down that mountain. If you're down here, oh, taking a picture, ooh, selfie, and then it just boom, it starts racing down the mountain super fast. You're here, you're pretty much incinerated. So it's that hot. And if you're outside the zone, like way, way out here, let's say, and you breathe this in, you can still burn your lungs from the gases in it, plus the temperature. And then you can also cut up your lungs because this is really, really fine pieces of material. You breathe it in, it goes into your lungs, and it can scar it and cut it. So you want to make sure you're far away from areas where there's these violent eruptions. This is super, super important. Okay, these are the big connections for today. What you need to know is that when you have this silica content, that kind of clear, light-colored mineral, when the magma is high in silica, you get a very thick magma. When it's low in silica, you get a runny magma. So when you have high silica, so it's really thick, it makes the rocks lighter in color. The silica gives the rocks higher viscosity. And so that's a term we're going to define and talk about. Okay, I'm going to go over viscosity just really quick with you. What is that? So you have a little bit of room on your paper here on that slide. Viscosity is the resistance to flow. So viscosity is a measurement, basically measures the thickness of fluids. So what we would say is the higher the viscosity, the thicker the fluid. So that's a direct relationship. As viscosity increases, the thickness of the fluid increases. So the opposite would happen, right? So the lower the viscosity, the lower the thickness. So here we have a milkshake. And then here we have a glass of Kool-Aid. So which one is higher in viscosity?
Milkshake.
Okay, so the milkshake. There you go. So really you're comparing fluids. One's higher, one's more viscous. If it's more viscous, it's thicker. Less viscous, higher in viscosity, lower in viscosity. So those are some terms that you'll hear. So when we have magma that's more viscous, you're going to get explosive eruptions. When it's lower in viscosity or thinner, you're going to have quieter eruptions. Okay? So make those associations. If it's higher viscosity, it's going to have more silica. If it's lower in viscosity, it's going to have less silica. So silica is the thickening agent. So what happens is you'll have, imagine, this is how it works. So you have these dissolved gases we talked about up here, right? You have all these dissolved gases in magma. What's that look like? So imagine if you have a bottle of soda and it's clear and you can see through it and you're looking at it and it just looks like water. I just see water in there. Yeah. And then you break the seal. What happens? Lots of bubbles all of a sudden. Where do they come from? You don't have bubbles. You break the seal. Bubbles. Where do they come from? The top, and then they, sometimes you have that air on the top. No, it was in there. They were in there the whole time. They were dissolved in solution. So what that means is as soon as you break that seal, you usually hear shh. This is under pressure. That soda was under pressure. So as soon as you break it, it changes pressure because now you're exposing it to the pressure of the atmosphere. So those bubbles, once they're not forced in solution, because you're forcing them in there, once you open it, they can come out of solution, those bubbles come out, the gas comes out of solution, and they'll bubble to the top because they're less dense. So that's what's happening in the magma. You have all these dissolved gases in the magma. So if your magma is thick, so if you have these vents, and you have these vents, and they have magma up top, you have bubbles coming up. Ooh, can't leave. This is really thick, high in silica. Just going to stay there. Ooh, more is coming. Ooh, more is coming. And then you get this pressure building up and all these dissolved gases, and you finally get just enough pressure to remove this high silica material, and then it goes really fast. So it takes all this high magma, lava material, and it just blows it to bits. And then it's showtime. Okay, so then you're going to have this huge eruption happen. Now, if it's thinner, less viscous, and you have these bubbles, they migrate up, oh, nothing can hold me back because there's not that much silica, so they just escape slowly. So you don't have that big buildup. So big buildup here, because it's thicker, it can hold back, take more pressure. Here, not so much. The gases are just kind of escaping, so you don't have those big explosions. So that's the difference between those two. Okay. So if you're looking at this type of volcano, what do you think? Explosive or quiet? Quiet, and why? Because it's flat. It's kind of flat compared to the other kind. And really thin liquid, you pour Kool-Aid on the table, it's going to go out as far as it possibly can. It's going to be really flat. You pour that really big milkshake on the table, it's going to build up a little bit. And it would, if it was magma, it would solidify before it had time to really move out. Okay? So this, with the Kool-Aid, it's just erupting and moving out. Now, the magma, this isn't the color of the magma. It's just showing multiple eruptions. So when you see these layers, it's just showing you, it's all going to be black because it's basalt. It's in the water. We know it's oceanic. So, but this is just showing it's had 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up. And you can count how many different times it erupted. It erupts, spreads out, next one a little bit higher over time. Again, same parts. You have your magma chamber, you have your crater, you have your vents, okay, you have your pipe. So you should get that on there. So you've got your shield volcano, and is that really fluid? Less viscous, runny material. It's mafic because it's high in magnesium and iron. Gas poor, meaning it's not gonna hold back a lot of gases. So we'll watch some of this basalt as it moves. Some of it can move pretty fast and some of it can move pretty slow. Like, yeah, I can outwalk that, whatever. And other times you can maybe outjog it or get in your car. But you can definitely usually outpace it. So let's watch video. So now that's just water vapor there. It's not those high gases, but water vapor does come out of magma. You can see it comes out. Pretty hot. Let's float. When you see the lava like this, the really light colors are hotter, warming up, and then you can see it's cooling fairly quickly because it's turning black right away. So that color is not scorched or burnt lava, it's that magnesium and iron that's in there. So you can see that it's moving faster because it's hotter, you have those lighter yellow tones, and then it starts to fold or bunch up there. It's not moving that fast. And these are pretty close up, so this isn't a huge the area. But it's pretty cool. Now that's moving pretty fast. Less viscous because it's moving faster, and because it's hotter, it's less viscous. So it's more runny.
Why is it white using it?
It's just hotter in color. It's a texture.
So if it's
Is there a cooler?
like this kind of like the hottest part.
Oh, like white.
Like white.
So the next one we're going to talk about is a cinder volcano. Okay, so we have cinder volcanoes. They're amazing. They're mafic with intermittent. So and you have these low, slow flows, and then they're intermittent, meaning then you're going to have these huge explosive eruptions. So it's like, what are we going to get today? What are we going to get this year? We're going to get slow. We're going to get violent. What's happening? They build pretty quickly. Their sides are super steep. And they have cinders, which are these rock fragments. So cinders are about this size, and they can get bigger, but around the size on average, like if you're walking down a gravel driveway, it's the size of the gravel, right? Somewhere in there. So imagine ash falling on you. Oh, ash is falling on me. This is awful, but I'm fine. But imagine cinders falling on you. So you want to really be away, far away from cinder volcano activity, especially when you have that volcanic type eruption. So there's a pretty famous one that happened in the 1940s, so we're going to watch that. And so look at the difference between a cinder and a shield. That was really slow, and this one happens pretty quickly.
What was mountain?
Mountains, the next one we're going to talk about, which is a composite or strato. Okay, this is going to give a little bit of a graphic reenactment, then we're going to watch live footage.
The Paracutan volcano is situated about 200 miles west of Mexico City in the state of Michoacán. The volcano was named for the small Tarascan village of Paracutan, which was destroyed by the volcano. Paracutan was considered to be one of the 7 natural wonders of the world because of the fact that mankind witnessed its birth. The volcano began as a fissure in a cornfield owned by a farmer, Dionisio Pulido, on February 20, 1943. By the end of 1 week, the cone formed from the earth stood about 450 feet high, and in 2 months it reached about 1,000 feet.
So he plants his before he even harvests his corn, boom, 1,000-foot tall volcano in his field. 2 months. That's shorter than your summer vacation. So it's really, really fast. These cinders grow super fast. And then it erupted. So let's look at some of the live footage. And some of the facts in the live footage aren't actually accurate, so don't listen too much to that. But we do have some live footage here, so.
Can we predict like where one of those will be born?
No, sometimes they just kind of come up.
In western Mexico, a new volcano comes to life. Huge columns of smoke billow skyward as ripping explosions within the fiery crater are heard for more than 100 miles. Molten lava pouring from the subterranean inferno buried a village of 600 people. The cone, after 3 days of activity, is 1,200 feet high. By night, the flaming lava presents an awe-inspiring spectacle. Explosions 30 times a minute. Amazing scenes of a phenomenon of nature.
So that one it grew really fast, it blew really fast. Now, about 8 years after that really explosive time, it just flowed lava for intermittently about 8 years. And then it's been quiet since like 1952. So, who knows? Maybe it's gone dormant. Probably not. We can't really tell yet. But it hasn't been active. Could it reactivate? They're kind of like a one-hit wonder. Like a song that's super popular and the band only sings one song. And they're super popular and they never sing another popular song ever. The one-hit wonder. That's pretty much what these cinder volcanoes are. They come up, they grow big, they do their show, and done. Okay? So now we're going to move on to composite and stratovolcanoes.
Is there a way that like if, let's say one magnitude creates the volcano and then it moves on and then the second magnitude comes it and it could not
Sorry?
So if there's two magma chambers, could it one create a volcano and then as it moves over and it does its thing, then the second one come underneath it and make the volcano not dormant anymore?
Yes. But it's unlikely. Because usually when it's dormant, the magma's done, it's gone, it's solidified. Now, you're kind of talking like a hot spot, but that stays active in the crust.
Or hot spot.
Yeah, it's a hot spot. The hot spots tend to stay active.
Yeah, it means there's two hot spots. Could one move over and become the hot spot a little bit, as it's in the middle of the two hot spots, and then come over and the hot spot. And react.
Yeah. Yes. Yes. I gotcha.